and thank you so much for having me at your event. I'm quite honored and grateful for the invitation to speak here. Many thanks to Andres for suggesting me and suggesting this, and Ed for organizing. So I was a data scientist for over a decade in various businesses down in Brighton. But since I started planning this talk, I have taken up a position as an AI consultant for Efficode. And what we're doing is guiding software development teams on agentic AI adoption. So I want to make it clear that I am not representing my employer here, and these opinions are my own, and they're not shared by Efficode, but they should be. Now, so let's start. The hype cycle is over. And as a job title, the data scientist title has lost its mojo. It's no longer getting called the sexiest job title of the 21st century, which I thought was fun while it lasted, but it's good to acknowledge that times have moved on. So data science outgrew an overhyped teenage drama and slipped down from under the spotlight, down into some dark valley of disappointment. But it climbed up and crawled up again, and now it stands as a fully grown-up professional on some middle-aged steps of blandness, flatness. And that is what I want to talk about. What is left after data science has shed all that manic hype and drama? What remains as its core value today? What is it that data science has got to offer? And to address that, it helps to have an understanding of the history that brought us here. So let's start there. Because in the beginning, the data scientist title suffered from a lack of definition, or maybe possibly too many definitions. So over my career of 11 years, every data science role I've held a handful of one, they've defined the role slightly differently from the others. And so I've had my own evolving definition. I'm sure many of you do as well. But that means that little could be said about the field that was universally agreed upon. And out of that vagueness of definition and lack of baseline, some imaginative conclusions sprouted and some inflated expectations as well. But data science, as a descendant of data mining, tended to be presented here like the region of the landscape of AI, with machine learning as its capital. This landscape is just littered with technologies and methodologies. And behind each of these words, there's a set of algorithms, libraries, tutorials, programming languages, and tools. And so even things that look like they are problem domains, like time series analysis or natural language processing, when you scratch beneath the surface of those terms, they are described and identified as solution tooling. Again, just a set of algorithms and methods and tutorials on how to do things. So, and libraries and courses. So during the peak hype era, I took and audited a number of online data science courses, and I sat in countless webinars, and I was consuming blogs left, right, and center, and following tutorials and YouTube videos and whatnot. And all of these focused on the how to do something. The focus was always on the solution, a method or tool. And this message was being hammered in, and the impression that you get is that data science was all about staying up to date with all the latest algorithms and methods. It's all about the tooling, the software libraries, the languages, R and Python and Julia, and then Rust, everything for the best optimizations for performance, speed, and memory. And your role models at the time were full stack data scientists, these 10x engineers and various influencers. And the message here is you are here to solve problems that are handed to you, defined outside your function. So the focus here is on how, and it never drifted over to why or even what questions to consider. And this famous Venn diagram that you've probably seen, it hints at the problem. So you see that two of the three spheres are technical, belonging to the solution space, the space of how to. And this is where the attention rested. Whereas the last one, domain knowledge, the business case, and the question why, this was neglected or seemingly forgotten. So even today, if you look and if you scan through Coursera or DataCamp or Udemy, they're all about the solution space in data science. So the crucial component had gone missing. This was supposed to have something to do with business problems, but the context was getting lost. But you might argue, okay, so what? Why care about that? Why do we need to care about the problem space? Why can't we just get the statistics, the mathematics, the programming right, the logic, and then we have a huge arsenal of tools and methods, and then we can tackle and solve any problem, right? You just tell us what you want, you bring your data, and we apply the rigorous methodology from our enormous toolbox, and out comes a model that we can then evaluate. We can evaluate for performance. We can fine tune hyperparameters until it's correct, and then we can deploy to production. If we just get the math right, then we know that we can trust the results, right? What's so wrong about that? Well, to be fair, sometimes it worked. Sometimes all that you needed was a straight line fit through some well-behaved correlated data observations with a high signal to noise ratio. And sometimes it was relatively easy to surface an existing and robust relationship between the features and the outcomes. And sometimes, if you were lucky, the model predictions produced this way helped your decision makers steer the ship past some rocky shallows or something. There were some highly touted examples of clever data science projects that saved the day for one business or another. However, many real-life business problems turned out to be a different sort of beast. They were complex, ill-defined, vicious, and resistant to these pat definitions. So methodology that had worked on one set of problems, the kind of problems that your data science certification course would be using, that methodology would fail and flail on a different problem set, the kind of problems that your business colleagues were tackling. We hadn't trained data scientists in mapping the boundary between those two cases. And many data scientists didn't have a good way of predicting which kind of problem their project would turn out to be until too late. So they were tackling someone else's poorly planned problems because they hadn't started at the right end by asking why. Why this project? What are we trying to achieve with this model? How does this relate to the business's bottom line? What decisions cost the business money when we get them wrong? And how can we help mitigate that risk or minimize that loss? And eventually, you get someone from the top floor down to the data science basement and saying, okay, show me the money. Or, can you just give me a measure of your bottom line impact? See, upstairs, they've been looking at the cost in terms of software systems, in terms of high individual contributor wages, in terms of training costs and conference costs and cloud data systems costs and etc. They have the costs down. Those were very clearly defined numbers. But where were the returns on that investment? How much money was made from your model running in production? Or how much money was saved? Was the business saved from by your model running in production? How much time and effort was saved, and at what cost of how much time and effort? And in business after business, data scientists lacked concise and solid answers to these questions. Again, there were loads of examples of data science projects meeting every requirement and expectation set for them. And some even had a story of returning value on the investment. And then out of that said, there was even a tinier minority that had the evidence to back that claim up. And this is especially true maybe in larger organizations and in tech organizations and forward-thinking organizations, and especially from problems of simple regression and classification of tabular data sets, and maybe some time series analysis as well. But the awkward truth remained that across the corporate landscape, a majority of data science projects failed. Models didn't make it into production even, or when productionized, they just failed to have a defined, measurable bottom line impact. So, oops, that was a problem. And so you all know what came next. Stained by commercial failures, the data science field lost the trust of the boardrooms, and the inevitable trough of disillusionment had some harsh lessons, and some not entirely fair, because it wasn't only the data science projects that failed. The return on investment was in question, at least, all across the data stack. And it was partly through data science, which was very hyped, that light was shone on the fact that, or was shone on the lack of data maturity in many organizations. So many companies, finally started to shift focus, towards their data infrastructure, their data engineering, their quality assurance, and the data ops and data governance. And these became hot new fields in the hiring space. And for advanced analytics, there was a new, fancier title that arose, unstained by the previous failures. That was the rise of the machine learning engineer. Now, take a step aside for a moment and just look over to our clever friends in the product teams and see how product professionals describe their roles. And note that the emphasis, 2 out of 3, is the domain understanding and user empathy. Those two lie in the problem space, and perhaps data scientists could learn something from that. If you talk to a product professional, this is where their conversation leads to. It's on those two spheres. But back to data science. As I suggested earlier, a good deal of the blame rests on the focus on the solution space. And data scientists got good at working at the granular level, but they didn't train in pursuing the questions that determine the success of projects. And that means questions like, what's the problem to solve? And I don't mean that in terms of the solution space domain. Like if I ask you what's the problem to solve and you tell me customer segmentation, no, that's not what I'm asking for. Or it's not customer segmentation or recommendation engine or revenue forecasting. You need the business problem under scrutiny. As an example, consider this problem statement. Our customers are churning faster than their lifetime value takes to overtake the customer acquisition cost. That's a very bad problem for a business to have, but it's a good problem statement for a data scientist to tackle. For one, there are 3 levers. There's churn prediction and churn prevention. There's lifetime value prediction and boosting. There's customer acquisition cost optimizer. There are different ways to tackle this. Now, the second question to ask is, why this problem? Sure, this problem is a problem, but where does it rank among the challenges that face the organization? Do you know which problems dominate the profitability of your employer? And then comes, what is the concrete question behind the problem? And is that a question that can be answered by available data? Considering that filters out projects or problems that lead to questions whose answers can only be attained if you have some imaginary or magical data set that's nowhere to be found. So don't waste your time on those. And then what is the value in solving this problem? What is the value of having a robust solution to this? Let's say you have one supported by statistical evidence. If the value is only X, that should put a cap on the level of effort that should be put into answering that question. You don't want to put in more money and time and effort in answering the question than the correct answer can give you back. And then how are you going to recognize and measure the success if and when this problem gets resolved? And then what properties must that solution have in order to be valuable? What accuracy must the solution have in order to be valuable? What's the precision or recall that is feasible and valuable? What does fit for purpose mean? Note that a shiny model with 99.9% accuracy might deliver the same or nearly the same bottom line value as a much more robust, simpler model with 85% accuracy. But the shinier model will be a lot more expensive for the business to achieve. Maybe the cost of false positives for a classifier is many times over the cost of false negatives. In that case, how do you balance the required precision recall? So it turns out that the real challenge in data science is properly defining your problem space. And that is ultimately just about being curious. It's about understanding the business you're in. It's to learn the business model. It's know where the revenue is coming from. Getting to know your customers, why, and understand why they choose your business. There are others. Know what challenges your colleagues are facing. See the friction that the various lines of business have to overcome for the business to run. And in particular, study the mechanisms that capture the data that you're working with. It's about asking questions and engaging with the stakeholders more usefully than by the people-pleasing servitude. You have to provide to them the grounding in reality of the data with all known defects and limitations that they rely on you for. And that means you provide data leadership, not just data services. And that is hard stuff. But that's the work. This is the work. This is what data science without the drama looks like. It's fully engaged with the real world complexities of business. And once you have that, once you know the purpose of your project, once you know the origin of your project and problem that you're working on, you will find that coding up the statistical model is embarrassingly easy in comparison. It's fun. That's the fun bit. But it's not the hard bit. For all intents and purposes, the algorithms they're solved problems. Most data scientists, unless you're at the very frontier research labs, you're not inventing the methods. We can all look up the solutions. We can download the libraries to use, or even entire code bases that do everything we need. And we can ask AI to help. It turns out that Claude Code, Codex, Gemini, CLI, they are absolutely brilliant at this. Once you have a principled understanding of the problem, you've solved the hard bit. And the rest of it, with the math stuff and the programming, the fun bit, that's easy. Now, caveat, you have the underlying training, but I'll assume that. So now if you allow me to, I'd like to share with you my definition of the data scientist role and do that in comparison with a machine learning engineer. And I want to preface this by stating I have no intention to spark a rivalry between the titles. I'm certainly not saying that one is more important or any other. I'm not making any statement about any given data professional with either title. And I'm sure the titles are loosely defined in most organizations anyway. But I do think it is elucidating to make a nuanced distinction between these two roles. To me, a machine learning engineer builds statistical models to solve defined business problems using machine learning, time series analysis, advanced analytics, and whatnot. Their models then, make predictions of future or unknown outcomes, and they fine-tune and optimize the models for performance. That includes the accuracy, precision, recall. That includes speed of inference. That includes size in memory, stability, robustness, maintainability, security. They bring a systems mindset to the problem, and they excel at thinking about how separate components interact in a system to optimize its function. And their emphasis is on technical optimization of the model. Now consider data science. If it is to be a science at all, a data science must involve the discovery of new knowledge, and that starts further upstream. It starts with an understanding of the business and its goals and challenges. And rather just receiving requirements from stakeholders, the data scientist should bring understanding of the properties of available data to define and rank problems facing the organization to reach strategic goals. The data scientists work with business stakeholders to develop the question and the requirements. And then depending on the question, there's a different machinery. It could be what caused this, diagnostic analysis, or it could be what's likely to happen next. That's predictive analysis. And what would happen to this KPI if we chose option B rather than option A? That's prescriptive analytics. Then the data scientist brings this product mindset to bear. They focus on the fitness of purpose of their models to the use cases, and then and the required features of a solution as well, as I covered. So the two roles, machine learning engineer and data scientist, they overlap across a number of tasks. They both handle structured and unstructured data, tabular data, or text, sound, images, and graph. They both tackle open questions using statistical modeling. They just approach these with very different mindsets. Where the machine learning engineer builds a statistical model, then optimizes the solution space, the data scientist focuses on clarifying the problem space and then builds the statistical model. Both have an interest in monitoring the model's performance after deployment. From the data scientist perspective, it's checking for model drift, how well it represents the world. The world is always moving. Is the model drifting? Is the model fit for purpose? And the machine learning engineer tends to focus on engineering performance, computational resources, timing, costs, security, etc. And there's another way you can crystallize the difference between the two, because engineering in general has this very useful concept of the minimum viable product, MVP, which basically means what is the smallest object that I can build that fulfills the requirements and works? What's the smallest thing that actually works? And product teams, they have this concept of minimum lovable product, MLP. And that means what is the minimum object that I can build and deliver that gets adopted and used by the stakeholder? And so minimum lovable product has a bit of a sappy name, but don't let that fool you. This is a concrete term, and this is key to having a business impact. And maybe the best way to understand the difference between them is to take the end user's point of view and never lose sight of the outcome of the model. So I strongly believe that data science should work with and learn from their colleagues in product. We should be asking them for the user stories behind our project, and we should be helping refine these user stories. Are these user stories that impact the company's bottom line, and how? So this is about focus on the end users and on the bottom line impact by thinking of yourself kind of as a product manager of your own data products. And which is because as we will see, this is where we're all headed anyway. Okay, so I am claiming that this is where the value of data science was hiding all along. And to recap, First, gain an understanding of your business's problem space. This means knowing what your business does and how it does it, why your customers chose you, etc. It's just elevating your thinking to strategic levels. And then engage with stakeholders and subject matter experts to understand their world and their pain points. Consider the hard questions that I listed above. Why this problem? What's the value outcome? And together with business users, what is the valuable concrete question that can be answered by available data? And as a side note, I can't see any way to achieve this without solid communication skills, which is another aspect of the data science field that is underserved by the courses and the training background that at least that I know. I haven't been in data science training for a while though. All right, but then and only then are you allowed to do the fun part where you get to play and experiment and throw the statistical, mathematical, and programming toolkits aside and onto the problem and question. And note that I am not talking about inventing any new types of problem to solve. Ultimately, the problems you end up taking on with this method, they're going to fall into the very familiar problem types. I'm just talking about intelligently discovering them, choosing among them, and accurately defining them. I'm just talking about ensuring the problems link to the bottom line outcomes that help the businesses towards their strategic goals. And it's worth noting that the connection between a data science project and the bottom line impact is sometimes surprisingly complex. And let's discuss an example of that. Let's talk about Netflix's famous award-winning recommendation engine algorithm. How did that project affect their bottom line? See, over a decade ago, this was the poster child for data science project. They even had $1 million award to anyone who could beat their algorithm for a while. Now, here's a question, a serious question. How successful would Netflix have been had they just had a very simple recommendation engine? Like one thing that would just show, okay, these are the top 10 content in your region for the last week, curated editor's choice, some randomized recommendations added, and maybe if you just watched episode 4 of a series, maybe just suggest episode 5 and be done with it. Consider when a user clicks on episode 5, was that because the recommendation engine suggested it, or would that user have gone there and found their way there regardless? Did they need a recommendation engine to go there? Is it just a convenience meaning? If a user finishes episode 4 and then it doesn't click episode 5, click something else, is that because they were bored with the series? Are they watching with a different family member, or is it because the recommendation engine was so insightful? And what is it that you want your recommendation engine to optimize for anyway as a business? If you're just trying to maximize Netflix's revenue, should the recommendation engine maximize the likelihood of a click? Should it maximize the spread of content that the user engages with, so that because that could, if they are middle of, rather than going through as a show, they are in the middle of multiple shows, would that not minimize customer churn? Or should the recommendation engine perhaps nudge the viewership for some curated content to go viral? Like if you want Stranger Things to be the things people talk about at the water cooler the following day, why don't we push more viewers that way? Or should the recommendation engine optimize commercial aspects of the content, like direct more viewership towards content that doesn't cost Netflix as much to provide? This question and these kinds of questions are very live with Netflix, with Spotify, with TikTok, and others. What is the goal of the algorithm? And to be clear, I don't know. I don't pretend to know what the answers are. And I'm sure Netflix has taken a very serious look into these kinds of questions and taking all factors into account. No idea what they actually concluded, but I do know that their content recommendation on my account are quite simple. There isn't $1 million algorithm behind it anymore. The narrative, but the point here is that the narrative from building a recommendation engine, the narrative pathway from that project down to Netflix's revenue is just not so simple. Now, let's talk about the kinds of value that a data science project can provide. And I'm going to rank them by bottom line impact. And the rule of thumb here is that the longer the narrative thread from the effort to the bottom line, the harder the sale is. And so at the top of the chain are projects whose successful completion directly increases revenue. Bringing in more money is the best way to get the attention and support of the executive suite. And here's a couple of examples. Let's say a new intelligent product feature that customers can be charged for specifically. So that would be new revenue stream. Yeah. And then another would be if you had an upsell recommendation engine that does a revenue uplift. And you could also think of, in this category, a logistical management data science project that prevents the loss of sales from running out of stock. So if you have your logistical management system optimized, you won't run out of stock, and you are not suffering the loss of corresponding loss of sales. So that's revenue protection. And then next come projects that reduce cost. And for the same profits, a business would much rather have a larger revenue at larger cost than a smaller revenue and smaller cost for the same profit. So revenue boosting is preferred over cost reduction. And within cost reduction, capital expenditure and operational expenditure savings are not equivalent. And the rule of thumb is that businesses like swapping CapEx for OpEx. So data science projects that offer savings on CapEx, capital expenditure, they're more desirable, but they're harder to achieve. Examples of CapEx reductions could be asset utilization modeling, like discovering and predicting underutilization of some expensive assets, and then replacing these with cheaper assets that are better fit for purpose. Another example might be predictive maintenance to optimize CapEx on equipment procurement. But in my experience, data science projects reducing operational expenditure are much more common. Examples include places where there's expensive friction or manual effort, and that's alleviated, like supply chain optimization or optimal treasury management. Next come projects that lighten the load or increase the capacity of available resources, meaning they allow the company to do more with less. And churn prediction is one example. And the idea here is that you focus your customer success team on the right handful of customers who are at risk of churning, and so that they don't have to waste time on the solid, happy customers intending to stay loyal. So your account managers can now keep a larger number of customers happy. But to justify this and to relate it to the bottom line impact, you now have to chain together, well, there's the model training and inference cost and the retention effort cost, the success rate, and then what is the false positive rate, and what is the extended customer lifetime value? What happens if you manage to predict that a customer is about to churn, and you interfere, and they stay on certain period longer, what is the value of that extra lifetime? But you can see now there's a longer narrative between the work and the bottom line. And next come risk mitigation and fraud detection projects. Now, to link these to the bottom line, you need to consider the cost of the effort of building the model, the cost of running it against all the transactions, and the cost of friction of false positives, that is, genuine transactions that are mistakenly identified as fraud, and the cost of the frauds prevented. So now the value case depends on the prevalence of fraud and the cost of the risk. So you might argue that this falls under cost reduction, and this is especially true when fraud is common enough, like it is in some finance and insurance organizations. But often the prevalence of the risk or its costs of fraud are just too low for automated detection and prevention to have a measurable impact on the bottom line. Now, on the bottom rung is the most common category. This is the category in which most data science projects fall. These are the operational optimizations. These range from detecting and discovering operational inefficiencies, efficiency boosters, productivity boosters. Now, this could mean pricing optimizations and forecasting workforce demand and many more. And what these have in common is that they have a longer narrative path from effort to value. Even when you've successfully built and deployed, the evaluation of the impact means you're comparing against the counterfactual. Let's take an example to clarify this. Let's say that we trained and deployed a model that computed the optimal price to charge for any product at any time. And it ran in production for a month, and the profits in that month were higher than the profits of the previous month. Yeah, hurrah, right? Bottom line impact, right? Higher profits. Okay, well, what were the sales? And what would the sales have been had we not jiggled the prices up and down the whole time? Did we trade more profits for fewer customers or more customers? What would how can we know that the profits were not affected by other factors, seasonality, the marketing campaigns, or that big deal that the sales people brought in during the period? The world's always moving. So how do you know that this was how do you know which part of the extra profits are attributable to your pricing jiggling? Now, it's unfortunately the case that this is the most common category of data science project, because this is the one that is hardest to prove the value of, and that often involves a comparison against a counterfactual. Now, I want to tell you quickly a story of a case study. And in basic terms, you have a company that had a workflow that goes like this. Data is generated. That data is used for reports, and the reports get delivered to customers. Now, sometimes the report is one of those weird and wonderful snowflakes that has to be customized for the occasion, a very bespoke report. But in other cases, it's of a standard variety and can be sort of deterministically or semi-deterministically generated from the input data. Now, when management analyzed the process, they found that more than half the reports were of the predictable standard variety, and less than half the reports were bespoke. And the effort involved was non-trivial. And sometimes reports took long, and customers were complaining that the reports were delayed. Now, what do you think happens next? Now, someone concludes that, hey, we should automate the manual effort and reduce the workload and improve efficiency. Bring in the data scientist to build this automation. Simple model was trained on a library of old reports and their input data to automate the filling in of a template of the standard report. Since this is customer facing, A human reviewer checks it before sending it into the delivery pipeline. Now, during development, the model had to incrementally take into account a number of considerations that were discovered. Like, for example, the report format had evolved over time, and the old reports had to be either dropped or tweaked before they could be learned from. And it was found that in actuality, it made sense to have a small library of templates and choose and fill in rather than have a master template and do all the steps on the master template. And although the content wasn't always the problem, sometimes the delivery mechanism depended on the customer. There were details like that to take into account. But eventually, all these challenges, they're not too unexpected, through time and effort and a little bit higher costs, the model eventually achieved very high accuracy and good reliability and was successfully deployed. So yes, happy days, right? Less human effort, same output. Efficiency goes up. Bottom line value achieved, right? Open the champagne. What could go wrong? Any suggestions? Well, as it turned out, there were complications. First of all, the model development and running costs, they had been greater than anticipated. So return on investment took longer to materialize. But the report delays persisted. And so the customers saw no benefits of this effort. The internal account management team were very dissatisfied with the changes. And that led to a deeper dive. And that revealed that, well, it was very rarely the standard reports that got delayed. It was almost always the bespoke reports. So automating the standard reports did nothing for the customers. The 40% of bespoke reports took so much longer than manually producing a standard report that the time saved on automating the work wasn't 60% of the account manager's time, but closer to 5%. They stated, but I think it was exaggerated. But in any effect, there was a big difference. And account managers complained that the time freed up by the automation had been the most enjoyable and productive time in their day, when they got the relatively easy task and satisfying feeling of getting things done. Now, in contrast, reviewing repetitive but machine-generated content proved to be an unpopular task. Imagine that. So this boils down to maybe not focusing enough on the bottom line, not understanding the end user, not getting the buy-in from the line of business, not bringing them along for the journey. Still, the model worked, and the process is now much more scalable with automation in place, right? However, making a process scalable is only valuable if the business then scales, and this business did not. This project did not return on investment. It wasn't the right problem to solve for that business at that time. Time and treasure were poured into something that could have been spent elsewhere, somewhere with someplace with a bottom line impact. Okay, so I wanted to close this talk with a comment on AI. I'm running a bit low on time, so I just want to run very rapidly through it. And the gist of it is that the story is repeating. This is exactly the same focus on what we're seeing in AI is the exact same focus on the solution space, and it is not necessarily well motivated, well thought through. It's hard to demonstrate the return on investment, and it's unavoidable. It's everywhere. It's changing our role. No matter what your old role was, you're changing it towards that of being a product manager over an AI system, and it's changing the emphasis of detailed work to emphasis of oversight and innovation. And it is increasing productivity for sure, and it is also reducing barriers to entry. But of all people, data scientists should be We should know and understand very well that AI tools are built on statistical models, and evaluating statistical models is in the data science wheelhouse. This is slightly different. It is different, but this is something that we should engage with pretty easily. But the point is, though, you're still going to have to focus on the correct problems to solve, not on the features of the solution. You don't get the luxury of choosing a solution, whether it's data science or whether it's AI, and then expect your problem space to adapt to the features of your solution. That doesn't work. So, okay, that's my time. I want to leave lots of time for discussions afterwards. So here is my summary. It's been a bumpy ride, and data science, the hype cycle is over, it's completed. The field has entered this plateau of productivity. It's become boring, and to me, that's great news. And during the peak hype, we had problems of people pleasing and overpowering focus on the solution space. This was detrimental to the field. And today, we can take lessons from the product professions and shifting towards the problem space, shifting our attention to the problem space, looking at the requirements, needs, and defining the right question and pushing back. Always start with a value measurement and consider the problem to solve. Avoid projects with a long narrative pathway between the work and the value. And for maximum impact, whenever possible, work on revenue boosting, followed by cost savings, and save others to last whenever possible. Now, and finally, the AI revolution is automating away coding and computing, making many roles less focused on the detail level. And that lifts our attention to the fitness for purpose and testing and quality evaluation and validation, and actually understanding what the solution is meant to do, what features the solution must have, rather than actually writing it. This is akin to transforming tech workers to product managers over the outputs of AI agents. And I am well aware that there is a lot of resistance, negativity, even sadness around this transition to be found. And some of that I find well argued and reasonable. But I, for one, I'm quite enthusiastic about this transformation. And that is what I think. Thank you for hearing me out. Now I would love to hear from you. Any comments and criticisms and clarifications, or even some questions. Over to you, Andres.
Well, Oscar, thank you very much for your talk. It's been great, and that's just what I was expecting. I think the data professional come with their own experiences, and it's by listening to them and the hurdles that they had that we can grow. I will be asking the questions from the audience now, so that people that will be kind of listening to the recording will know the context. So the first question is regarding the neglected questions that you talked about earlier on. Any thoughts on how to quantify some of the things being asked for?
Quantify the effort of these questions, or sorry, to quantify.
I was thinking at the impact,
the
but the
impact.
effort is also.
Yeah.
Let's see if the.
Yes. So the questions. Let me go back to them so that we can see them as I speak about them. To me, the questions are ordered in sort of chronological order, and in terms of ranking them by impact. What's the value of solving this problem is the core of it. If you have a good conversation about what is the value that you will get out of the solution, that is often, I think that if you're only choosing one of these questions, do that one in terms of impact. And that's not just data science. Actually, I was doing business intelligence for a good while, and you would get stakeholders asking you to, oh, can you calculate this number? What is the average basket value in this region or something like that? And I would sit down with them and say, okay, I can do that. I know where the data lies and where how and transformations and calculations that need to be done and how to deliver that. But my question to you is, let's say the answer is 42. What is your next move? What do you do differently now that it's 42? The answer is 42. Now what do you do? Push it back to them. What is the value of me running around and answering these questions? Because the experience of doing that, the servitude, is that there's another question before I get back there. There'll be another question and another question. And so yes, so that would I would put highest value on that.
Thank you, Oscar. I have a question of my own before I'll come to the other questions from the audience. You talked about the ranks in the kinds of value. I think it's the slide just before this, or maybe a couple of slides. Where would you say that most of your own work was? And if it was in
I
the
see what
ones
you're
with,
saying. Are we
yeah,
talking?
yeah, yeah.
You're
The next,
talking about the
yeah, this one.
yeah.
So where would you say that most of your work was? Did it change? What can we do about it?
So when I say that operational optimizations are the most common data science projects in my experience, I'm not just referring to the problems that I've worked on myself. I'm also talking in terms of problems that you see in the data science literature, in the coursework, in the tutorials that you find. Here's how you do this. Here's how you do it. It tends to be these operational improvements in my experience. It's the kind of thing that is super cool. If I could do this, if I could calculate this and show this for any company, and I feel like, oh, that'd be great. And I still do these tutorials. I do still love these tutorials. But my next question is, what company can convert that answer that I would give them, that model that I would give them, that system that I build on that to bottom line value? What you know uh, what needs to happen for that to make a company more money? And that's a tough question often.
Thank you, Oscar. I'm going to pick another question from the audience. It's about what we hear all the time, that we need data scientists for big AI projects. What about machine learning engineers? Do you think that they are as important as a data scientist, or can we do without them?
No, 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 no. So yes. So if the project has been well defined and its pathway to value is clear, and that work has been done, what you need is a machine learning engineer. And this is especially true in enterprise where you have deployment and security and governance issues alongside. And I think that's where where the machine learning engineer excels. It's for most businesses that have much more vague feeling about something that's missing, something that they want added, or some feeling that there is an inefficiency somewhere. They haven't fully defined the problem, and that's where my definition of what a data scientist fits into that slot. Now, if you look on LinkedIn, people use machine learning engineered data scientist or AI. They use it more or less interchangeably. We need an AI person to help us draw a line through a data set.